Now, the first question I want to ask is, so there are about 4 different distinct ways a function can fail to be differentiable. So let's discuss the first one. So, question. Is there a relationship between continuity and differentiability? So what do we think? So remember, differentiability means that there is a derivative there, and continuous means that the limit of the function equals the function value. So Yana, you said to be differentiable, a function must be continuous. Okay, so that is the correct relationship. In other words, continuity is a necessary condition for differentiability. It's not sufficient, right? We've already seen a function that is continuous but not differentiable, right? Absolute value of x. That is a continuous function, but is not differentiable at x equals 0. So continuity does not guarantee differentiability, but you must have continuity if you have any chance of having differentiability, right? I mean, if you think about it, it kind of makes sense. I mean, the proof is in the book. It's a very simple proof, but we won't actually go through it. But the idea is if I have a discontinuity somewhere, how can there possibly be a tangent line there, right? The function doesn't even meet up at some point. So if you have a discontinuity, you cannot have a tangent line there. There's no slope there. So continuity continuity is necessary for differentiability. So if I list all the ways a function can fail to be differentiable, what is one way a function can fail to be differentiable? It can be not continuous, right? So to say that differentiability implies continuity, right? Logically, so in case no one has ever told this to you, so right now we have, if something is differentiable, it must be continuous, right? Okay. So when you have an implication like this, something implies something else. If you swap the two orders, first of all, that is a different statement, right? If it's raining, I need an umbrella. It's not the same as if I need an umbrella, then it's raining. It's not quite the same thing. However, if you switch them and negate both of them, it's the same. Logically, it's equivalent. So not C implies not D, right? So if I don't need an umbrella, then it's not raining, right? That is the same thing as saying if it's raining, then I need an umbrella. So in other words, differentiability implies continuity, and that's the same thing as saying not continuous implies not differentiable. So that's what we're going to write here. So if f is not continuous at x equals a, then f is not differentiable at x equals a. Again, the reverse does not hold. A function can be continuous but not differentiable. So now let's see the other ways. So what if f is continuous? So if f is continuous, how can f fail to be differentiable? And there are 3 distinct ways this can happen. So we've already seen one. We've seen one example where we have, say, a corner. Right? And an example of that is absolute value of x, right? So absolute value of x is kind of a prototypical example of a function that has a sharp corner, and so at that corner, the function is not differentiable, right? Because there's a sudden change in these slopes. Now, there are a few other ways this can happen. So here's another corner. So let's also draw, let's see what I want to draw here. So this is also, so this is another corner over here. This is called a cusp. A cusp is not quite a corner. A corner, if I take the derivative on both sides, I still get a finite slope, right? I have kind of a slope from one end, a slope from the other end. A cusp is different. If I were to look at all the tangent lines here, they approach a vertical line on both sides. So a cusp actually is a point where the derivative becomes infinite from both sides. And a function that kind of looks like this is a function like x to the 2/3. And then finally, the last way a function can fail to be differentiable is if I have, say, a vertical tangent line like this. So this is again where the tangent line becomes vertical, but it's the same infinity from both sides. I mean, the exact definition of cusp and vertical tangent, you don't really have to know, but you should be able to recognize these graphically. So this is a vertical tangent. And a function that has that feature is x to the 1/3. It has that vertical tangent feature. So if you were given a graph of a function, even if you don't have a formula for that function, you should be able to recognize graphically, point out all the x values at which this function is not differentiable. So in other words, this function would not be differentiable at any of these marked x values, x1, x2, x3, and x4. Okay, and you should be able to briefly explain why. And it's enough to say there's a corner, there's a cusp, there's a vertical tangent, right? Anything like that. Or the function's not continuous, right? Don't forget about that condition also. If a function is not continuous, it's not differentiable. Okay, so that was just the one last thing that we had not done in the last lecture.